Hello, student. Precalculus, Chapter 3, Section 1 and 2. Exponential and logarithmic functions. So far, we learned about linear function, which is the line, and squaring function, which is parabola, a U-shape, a cubic function. It's all like having x to power, x to power, x to power. And here is different. Exponential function. I'll give you an example. Okay. If I write y equal a to power x. Now the x is the power. That's what we call exponential function. Or you can say fx is equal a to power x. One thing here important, a cannot be zero because become meaningless. A should be greater than 1, positive greater than 1. Because if it's 1, it doesn't mean anything. It's just 1 to power x is 1. Where x can go from negative infinity to positive infinity. No problem. How much the y value? Because a well, y value, we'll find out y is always greater than 0. It's positive. Okay, greater than 0. Example, like in your calculator, you must find a function said shape a button. They show you a to power x, or they may say x to power y. They may say x like this. That means to power. Okay. So we need to try this function. Find the value of 2 to power x, where x equal negative 3.1. So basically, in your calculator could be looking like this: 2 up caret negative 3.1, something like that. Then you get the number. Or maybe 2, and you push the button y to power x. Then you say negative 3.1. So you do the same thing for this one, 2 to power negative x. You put pi. That means, let's see, they have an answer here in the next page. So 2 to power negative 3.1. That was showing you. This is maybe in your calculator. You get the answer. You need to figure out how to use your calculator. 2 to the power negative pi, we say 2 to the power negative pi. Now you have 0.6 to the power 3 over 2. Right here, when they said 0.6 to power, we use parentheses. So this way we have to do this operation first. 3 divided by 2 is going to be 1.5. Then we say 0.6 to power 1.5. Let's notice something in here. When the power is negative, okay, so if we have a to power x, if x less than 0, negative, y is greater than 0. We said y is always positive. Why is that? How come that? How is that possible? Let me show you why. When the power is negative. So if we look 2 to power negative 3.1, that should be equal. If this is gonna have a bottom, let's say make it a fraction that has a bottom 1. I'll reverse it, leave 1 on the top, and then the bottom. If I move this to the bottom, it becomes positive power. Now, what the answer of this is going to be less than 1 and positive 0.1166. So when you have a power is negative, you always move it to the bottom and become positive, and will cause the answer to be very small because you are dividing by a big number. Okay. Now, if it's positive, it's going to stay positive. If you say 2 to power 3, that's going to be 8 as positive. So that's the reason y is always positive, will never be negative. Graph of exponential function. We're going to make a table. So we have two examples, 2 to power x and 4 to power x. Oops. Here we go. We make the table. This x value, negative 3, negative 2, negative 1, 0, 1, and 2. If we plug 2 to power x, remember, we said 2 to power negative 3, that's equal 1 over 2 to power 3. That will give you 1/8. That's when we got the 1/8 from. For 4, you say it become 4 to power negative 3 is equal 1 over 4 to power 3. Well, how much is 4 to power 3? 4 times 4 is 16, times 4 is 64. Same thing in here. 2 to power 3, we got 8. So that's the reason we got here 1/8, and here 1 over 64. When you go to negative 2, you get 1/4, 1/16, then half, and 1/4. When 0, both of them, they gave me 1. What? How come? We got the same answer? Well, we know that. Remember that any number to power 0 equal 1. So that's the reason 2 to power 0 equal 1, and 4 to power 0 also equal 1. So that's we got the same answer. Then when we go to 1, 2 to power 1 is 2, 4 to power 1 is 4. 2 to power 2 is 4. Then 4 to power 2 is 16. If we plot this point, we get those two graphs. And as you see that when x negative, The y is very, very, very small. Y is less than 1. Less or equal 1. When x negative, y is less or equal 1. So we intercept here with y equal 1. Even like for 4 or 2 to power, they are on top of each other almost. Okay, so less than 1. Still positive, but less than 1. Now, when x is greater than 0, then y is greater than 1 and start to increase dramatically. That's the reason we call it exponential. We say, well, I increased exponentially. That means I started slow, then I ended up faster. So like sometimes that's a learning process. Well, I start slow, then I exponentially finish the course. We already went through these. Always we have the y-intercept is always 1 with y. Always y-intercept 0, 1 for any exponential. So here we're talking about a to power x. So a to power x doesn't matter what the value of a is, still we have the y-intercept is equal 1. And as we said, like when x negative, these numbers, they get very small, less than 1. What would happen if x equal infinity? Y equal a to power infinity. What does that mean? As equal infinity. So we're talking here in this area. So this point here, infinity, comma, infinity. Okay. Now, if I am at the negative infinity of x, so if x equal negative infinity, so what's y equal to? It's equal a to negative infinity. Well, otherwise, we'll move it down. We have 1 over a to power infinity. You get 1 over infinity. How much is that? Any number over infinity equals 0. Okay. So we have a point x equals 0, y equal infinity. What kind of this is that mean? At the infinity, and the way we draw the line here, we left a gap. This gap meaning that we have a point at the negative infinity. That's 0, comma, negative infinity. It's so far away, it's come out of the paper. I cannot even draw it. So that's going to be going forever until they meet. So the graph and the x-axis will meet somewhere far away. So because of that, we're going to call x-axis is an asymptote. Horizontal x-axis is horizontal asymptote. Okay, that means a to power x approaching 0 when x going to x negative infinity. So what is asymptote? Let's write it a different way. Asymptote, we're going to see a lot of asymptote later on, is a line that meet the graph at infinity. Okay, so that's the definition of asymptote. So I can have a different scenario for asymptote. Let me see. If I have a gap, well, all right. So if I have a line like this and I have a graph like that as an asymptote, if I have it vertical and I have a curve like that, that's also asymptote. So anytime we have a point meeting a line at the infinity, we call it an asymptote. If a line like this is an asymptote in any direction, as long as we draw it in the same manner. Well, this is a graph for a to power x. Can I do y equal to power negative x? Yes, what's going to happen? The graph will flip to the other side. So this is the y equal a to power negative x. So the asymptote as a positive, we have a 0 comma positive infinity. Okay, and this point go to negative infinity, positive infinity. Okay. Let's see, I think that's going to be in the, oh, here we go. That's in the next page. Still, the y-intercept did not change because a to power 0 is always 1. A to power 0, always 1. Here's the asymptote. The x, this is 0 comma infinity. And this function decreasing, it's going down. The other one was increasing. One-to-one property. You're going to use this a lot, extremely important. What they are saying here, if I have a to power x equal a to power y, then x equal y. I'm going to rewrite it a different way in global. This is kind of specific. It doesn't have to be x, could be anything. I can say here a to power anything, could be big formula, equal a, has to be a, same base. Whatever inside, I'm going to say if base same is the same, then power is the same. Is the same. Okay, what does that mean? We're going to say whatever in the power equal whatever in the power in the other side. That's called one-to-one properties. Small example here. If I say 4 to power x squared equal 4 to power 16. What is x? Well, the base is the same. You say x squared equals 16. Then x equal positive negative 4. This way we solve for x. So we don't need to worry about taking the power. If the base is the same, then the power is the same. Natural base E. E is a special number. Some scientists found about it have special properties. So they used it to simplify some stuff in finance and mathematics. E is basically is a number. E is a number. If you push in your calculator, you have a button e to power x. If you put 1 and push e to power x, then you're going to get the answer e equal 2.71. I don't know how much. So that's there's about 7-8 numbers. Normally 2.71 should be good enough for hand calculation, but if you push it in the calculator, you can get the number by put 1 and push e to power x. Then you're going to get the exact answer. Well, this number, so we're going to have a function y equal e to power x. Well, is that different from same as a to power x? There are no changes in the property. Whatever we said about a to power x, we apply it to e to power x because e is a number here. You can see like for e to power x, same thing. It's gonna a smaller number in the negative side, x less than 0. And always the y-intercept is 1. Always is 1. If you do e to power negative x, it's gonna flip. Also, x is the asymptote. The same thing. I'm not gonna say that again because they are same properties. And like I was seeing the number, you can see that they're almost the exact number. Maybe better to approximate it 2.72. You get better approximation. This is to practice your calculator. If you say e to power negative 2, remember, if your power is negative, your answer is less than 1. Same thing, e to power negative 1, this is normally equal 1 over e. You do that in the calculator, you get 0.36. They are telling you what to do to get, so you have e negative 2. You push the e to power x, you push negative 2, hit enter, you get the answer. Now, e to power quarter, here the power is positive, then the answer most likely, sometimes it could be less than 1, but here it seems like it's more than 1. So in general, positive power is always greater than 1. When the power is negative, your answer's less than 1, less than 1, less than 1. You can see 3 examples of power is negative. Well, that's the end of section 1. And that's a formula here. I'll show you how did they got the A. Don't worry about that part. This is financial problem. Let's go to section 2. Logarithmic function and their graph. I'm going to rewrite the exponentials this way. If x equal y, a to power y, a to power y, that's exponential function, but it's kind of reverse the names. That will allow us y equal logarithm base a of x. These are equivalents, represent same thing. Same thing. Actually, we'll see later on, exponential function like that and logarithmic function like that, they are flip-flop, they are symmetric about a line. We're going to see that drawing in a minute. But whatever x here, that's the same x. A, same A. Y, same A. Here we say exponential, here we say logarithmic function. For logarithmic function, we have same restrictions that x must be greater than 0 and a must be greater than 0. All right, so here we go. We have the logarithmic function with the exponential function, relative exponential function. Let me give you here an example. If I have 2 equal log base 3 of 9, convert to exponential, go from here to here. Well, the easiest way for me, because this is logarithmic, I'm going to write, put y, small y here, and put a here, and put x here. Then rewrite this formula again. So this is x equal a to power y. How much is x? Is 9. How much is a? Is 3. How much is y? Is 2. Well, that's correct. 9 is equal 3 to power 2. Very easy to change. If I have another example, 125 equal 5 to power 3. So this is exponential form. Because 5 times 5, 25, times 5, 125. Convert to logarithmic log. Same thing, what I'm going to do, if I look at the x equal, so this is x equal a to power y. So based on that, when I'm going to write y equal log base a of x, how much is y? Y is 3. Okay, this is the y. How much is the a? A is 5. How much is the x? 125. So that means 3 equal logarithm base 5 of the number 125. That's in logarithmic method. So it's easy to convert between those two shapes by understanding. Always keep in mind you have this formula in your formula sheet, and you just look at it and figure out how to go from this to this or from that to that. Well, they said this is logarithmic, right? This is A. This is, so what was the formula? If you forget it, just write it down. Y equal logarithm base A of X. So that means this is A, this is X, and this is Y. If I have to write it in exponential, I have to say X equal A to power Y. So how much is X? Is 8. How much is A? Is 2. How much is Y? Is 3, which is correct. 8 is equal to power 3. Examples. Evaluate for the given X. So the first one, A, we have, I'm going to write it as Y here because it becomes confusing. So I have Y equal log base 2 of X, 32. So I'm plugging 32 for the X and converting this to be a Y. Now, I'm going to convert this to exponential to find the answer. So always write them down here. Y equal log base A of X and X equal A to power Y. So based on that, if this is Y and this is A and this is X. So X 32 equal 2 to power Y. All right, what's the benefit? Still, I don't know what the value of Y. Well, we need to use one-to-one formula. If I have A to power anything equal A to power anything else, then these are equal, right? Well, do I have it here? Not yet. Can I do that? Can I convert 32 to 2 to power something? That equal to the 32? What is this number? 2 to power 2 is 4. 2 to power multiply by, so multiply by 2 is 8. That's 3 times. Multiply by 2, 16. Multiply by 2, that's 5. So this should be 2 to power 5 equal 2 to power Y. Then guess what? Because the base is the same, that means Y equal 5. Okay, 2 to power 5. So we got the answer. Here you have to kind of go back to your calculator and figure it out. Or you can do it in your head. You count how many times you do the multiplication. You say 2 times 2 is 4, times 2 is 16, is 8, times 2, 16, times 2 is 32. That means how many times? Is 5. Then I said 5. Let's do the next one, B. Y equal log base 3 of 1. Let's convert it. This is Y, this is A, and this is X. So we're going to say 1, the X equal A, which is 3, to power Y. Oh, this is seem like hard. Remember, I have to convert this one to 3 to power something equal 3 to power Y. But 3 to power something, it should be equal to 1. What is this question mark for this to equal 1? All right, reminder, any number to power 0 equal 1. To power 0 equal 1. Well, the only way I can get 1 if it's 3 to power 0. And that's equal 3 to power Y, then Y equals 0. Solve the problem. C. Y equal, I'm changing the fx to make it simpler. Y equal log base 4 of x. That's another tricky one. A, oh, I need to, what's the A? Oh, this is 2. Let's put 2. And this is the x. Then I have to write 2 equal 4 to power y. My goodness. Again, I have to say 4 to power something that's equal 4 to power y. Well, remember, this should be equal to 2. What kind of power is that? Well, this is the square root of 4 is 2. That should be written 4 to power half equal 4 to power y. Okay? Because 4 to power half means square root. 4 to power half equals square root of 4. And that's equal to. Now y is equal half. Well, the last one is a little bit harder. D, we have y equal log base 10 of 1 over 100. So we plug the value of x. Let's do the same thing. This is a, this is x. So you have 1 over 100 equal 10 to power y. This problem here, kind of have to use common sense. You can see some relation between 10 and 100. Can I rewrite this one 10 to power 2? Because 10 to power 2 is what? 100. Then what we get, 10 to power y. Now I can take this one to the top, it becomes negative 10 to power negative 2 equal 10 to power y, then y equal negative 2. We solve the problem. So each problem has different flavor. Here's a nice table that's comparing logarithmic to exponential. That log base a of 1 always 0. It doesn't matter what's the value of a. And the same thing, a to power 0 equal 1. Remember, also e to power 0 equal 1. Now, log base a of a is equal 1. Because a to power 1 equal a. Like e to power 1 is equal e. So really important to remember, when you have the base equal to the number I'm looking for, so log base a of the same value is going to be 1 always. Now, those here very important, 3 and 4. Log base a of a to power x equal x. And a to power log base a of x also equal x. We call this inverse properties. We learned that at the end of chapter 1. Okay, extremely important that you remember that. So log base a of a equal 1. When I say power x, then the answer is x. Now, hey, a to power log base a of x is also x. Now, one-to-one property is very similar to the one we saw a minute ago. We have log base a of x equal log base a of y. Because the base is the same, that what's inside is the same. Remember, we have a to power anything, well, a of anything else. That means those are equal. Now, what we're saying, log of base a of anything equal log base a of something else, then this also equal. Okay. Graph of logarithmic function. We can make a table, same way we did. Here they are comparing 2 to power x to log base 2 of x, because those they are cousins. They they represent same things. So they have a table here. X, -2, -1, 0, 1, 2, 3. We get all the value for 2 to power x. For some reason, they didn't do the table for the log base 2 of x. If you do that, you can do it. Right now, we don't know how to do it. Later on, we'll learn how to do it. I think that's the reason they didn't tell us, they didn't make the table. So basically, 2 to power x and log base 2 of x, they are symmetric about this line. It's our same thing. So we have, this is the asymptote, horizontal asymptote. Now the logarithmic have a vertical asymptote going down to infinity, negative infinity. As I said, we have a vertical asymptote at x equals 0 because of this y meeting the graph at the infinity. But they always have x-intercept is equal to 1. So in logarithmic, if I set y equal to 0, so log base a of 0 is equal 1. Okay. You can see here's a drawing, log base of x. That is always same point. Doesn't matter what's the value of a. We have an x-intercept. So what's this point mean? That means log of 1 equals 0. Doesn't matter what is the base. Oh, we have, remember, we have also natural logarithmic functions. If we said x equal a to power y, and we said y equal log base a of x. Now, if we say x equal e to power y, then y is equal log base e of x. That's called natural logarithmic. This is called natural logarithmic function. Same thing. And all what we did, we take the a, we put an e. Same principle, same graph, same theory. Is nothing new. The only thing is new is the name. Okay, well, there is something here is kind of a little bit confusing. We need kind of get our brain to learn it. In your calculator, you're gonna find a button have only log, no a. Mean, what does that mean? Or implied that log base 10. That's automatic base 10. They are not going to tell you base 10, but it is base 10. If you see this symbol, that's a confusing part. LN. LN mean log base E. So they took all of this written and make it that simple, LN. So if you see that button in your calculator, that means natural logarithmic. That means log base E. Keep in mind, that's log base E. If you forget, always write it on the side. So when you do your work, say this is log base E. So you know what you're doing, because sometimes you forget. It's the shape a little bit confusing. Base 10 is easy to remember. We said they repeat the same thing, that they are symmetric, logarithmic, and exponential. And here example to practice for natural log. So if you want to practice these things, you say natural log 2, hit enter, you get the answer. Natural log of 0.3, you hit enter. Now here is a problem. If you use negative number, you're going to get error. For any logarithmic function, no log or ln for negative numbers. Okay, there is no log for negative numbers. And you could do an equation that's like 1 plus square root of 2, and you do the natural log for it by using parentheses. Here's also a table for natural log, which is similar to base A. We said log base A of 1 equals 0. That's the same thing. This is mean ln, remember, ln is equal log base E. You need to remember that. So if I put base E, as will give me this one. Now natural log of E is 1. That's the same thing when you said natural log A of A, also 1. That's the same thing. So if I say natural log base E of E is equal 1. Now, if I say natural log of E to power X, that equal X. And that was, what was it? Log base A of A to power X, that's equal X. That's called inverse property. At the same time, we have E to power ln X equal X. Same thing if we say A to power log base A of X equal X. One-to-one property, we just did that. If we have a natural log equal natural log, then whatever inside they are equal. Or you can say natural log of anything equal natural log of anything else, then the inside they are equal. The minute you understand, it looks like a lot. The minute you understand the principle, they are the same, but with different shape. Well, that's the end of section 2. Some application here. Let's see if there's any exercise we can do. It's a good idea to practice immediately after you listen to the lecture. 3.1. Oh. Well, we cannot do this exercise until I do section 3. Okay, so let's wait until we do section 3. You can do that one, or you can go back to your homework online and you can find and practice there for the section 1 and section 2. Because section 1 and section 2 they are the basics. We'll stop here.